Hello, and welcome to Sleep Archive. In the time that follows, we will trace the magnificent and enduring life cycle of the stars, observing the slow transformation of simple gas into the brilliant engines of the cosmos. As you listen and rest, we will explore the forces of gravity and nuclear fire that define the history of every sun, beginning our journey in the deepest silence of the interstellar void. To understand the life of a star, we must first look to the places where light has not yet reached, the immense and cold reservoirs of the galaxy. Our journey begins in the cold, silent reaches of interstellar space, within the vast and sprawling structures known as giant molecular clouds. These clouds are the quiet cradles of the universe, immense reservoirs of gas and dust that can stretch across hundreds of light years of the galactic disk. Despite their name, these regions are almost entirely composed of molecular hydrogen, the simplest and most abundant element in the cosmos. The environment within a molecular cloud is one of profound stillness and extreme cold, with temperatures hovering just a few degrees above absolute zero. At these temperatures, the thermal energy of the atoms is so low that they move with a slow, heavy grace, allowing gravity to begin its patient, multi-billion-year work. The structure of a stellar nursery is not uniform, but is characterized by intricate filaments and dense clumps of matter that weave through the dark like smoke. These filaments are created by the subtle interplay of magnetic fields, turbulence, and the collective gravitational pull of the cloud's immense mass. For millions of years, a molecular cloud may remain in a state of quiet equilibrium, a dark silhouette against the background stars of the Milky Way. However, the balance is delicate, and the birth of a star often requires a catalyst, a gentle nudge, to overcome the internal pressure that keeps the gas from collapsing. This catalyst might be the shock wave from a distant supernova, the gravitational pull of a passing star system, or the slow compression caused by the galaxy's spiral arms. Once a region within the cloud becomes sufficiently dense, it reaches a tipping point where its own gravity becomes the dominant force. The cloud begins to fragment into smaller, localized pockets of matter, each one destined to become a separate star system. In this moment, the architecture of the nursery changes from a singular, sprawling entity into a collection of individual, collapsing cores. As a core begins to contract, the atoms of hydrogen are drawn closer together, and the potential energy of their position is slowly converted into kinetic energy. The center of the core begins to warm, even though the outer layers remain frozen and dark, shielded from the light of the rest of the galaxy. This process of collapse is not a sudden event, but a measured and steady progression that defines the first stage of a star's long existence. As the matter falls inward, it begins to rotate, a consequence of the slight original movements of the gas within the larger molecular cloud. This rotation causes the collapsing core to flatten into a disk with a dense, glowing concentration of mass forming at the very center. At this stage, the object is still hidden deep within its cocoon of dust, invisible to the eyes of any distant observer using ordinary light. The dust particles, microscopic grains of carbon, silicates, and ice, absorb the energy from the warming center and re-emit it as infrared radiation. If we were to look at a stellar nursery through an infrared lens, we would see these dark clouds glowing with the heat of 1,000 hidden fires. The structure of the nursery is now one of transition, where the cold, diffuse gas of the interstellar medium is being refined into something far more concentrated. Within these dense cores, the density of matter increases by many orders of magnitude, creating a pocket of high pressure in an otherwise empty universe. The gravitational pull at the center becomes a powerful anchor, drawing in more and more material from the surrounding envelope of the original cloud. There is a sense of inevitability in this process, a movement toward a focal point that will eventually lead to the ignition of a star. The surrounding filaments of the molecular cloud act as conduits, feeding the growing cores with a steady stream of hydrogen and dust. The scale of these structures is immense, yet the focus of the universe is now narrowing down to these small, hot centers of activity. As you visualize this stellar nursery, imagine the vast, dark clouds of the Eagle Nebula or the Orion Complex, where new suns are currently taking shape. The air, if there were air to breathe, would be thinner than the best vacuum we can create on Earth, yet the sheer volume of the cloud ensures it contains the mass of millions of suns. The silence of the nursery is absolute, a quiet that is only broken by the slow, gravitational shifting of trillions of tons of matter. Every star that has ever shone, including our own sun, began its life in a place exactly like this, surrounded by the cold and the dark. The architecture of the stellar nursery is the foundation for everything that follows, providing the raw materials and the initial conditions for the life of a star. As we move deeper into the heart of a collapsing core, we see the temperature continue to rise as the density reaches a critical state. The core is no longer just a collection of gas, but is becoming a singular, distinct object that is beginning to assert its own presence in the cosmos. The transition from a cloud to a star is one of the most fundamental transformations in the structure of the universe, a victory of gravity over entropy. The nursery remains a place of mystery and potential, a storage vault for the building blocks of planets, moons, and life itself. As we observe the slow contraction of these filaments and the glowing heat of the central cores, we prepare to witness the emergence of the protostar. The journey of the star has begun, and though it is currently shrouded in shadow, the first light is nearly ready to break through. The stillness of the molecular cloud is the quiet before the most energetic processes in the universe take hold, a calm and steady beginning to a magnificent cycle. We rest our attention on the dark beauty of these gas clouds, acknowledging them as the ancient and enduring guardians of the stars. As the collapse within the molecular cloud intensifies, we enter the phase where a distinct, singular entity begins to emerge from the darkness, a structure known as a protostar. This stage of stellar evolution represents the transition from a diffuse collection of gas to a concentrated object that has begun to develop its own internal identity and gravitational authority. The protostar is not yet a star, for it has not yet achieved the ability to generate energy through nuclear fusion, yet it has become a powerful source of heat and light in its own right. The structure of a protostar is characterized by a central, glowing core surrounded by a massive, rotating accretion disk of gas and dust. As gravity continues to pull material inward, the potential energy of the falling gas is converted into thermal energy, causing the temperature at the center to climb toward millions of degrees. This heat is generated entirely by gravitational contraction, a process where the crushing weight of the outer layers compresses the core into an ever denser state. At this scale, the protostar is often hidden from our view by the very material it is consuming, shrouded in a dense envelope of dust that forms a cosmic cocoon. Within this envelope, the central object is growing rapidly, pulling in more mass from the surrounding disk through a process of accretion. The conservation of angular momentum ensures that as the core shrinks, it spins faster and faster, much like an ice skater pulling in their arms to increase their rotation. This rapid spinning creates a powerful magnetic field that interacts with the incoming gas, leading to one of the most striking features of the protostar, the bipolar outflow. Powerful jets of ionized gas are ejected from the poles of the protostar, shooting out across light years of space at incredible speeds. These jets act as a release valve for the intense magnetic and rotational energy building up at the center, and they create vast glowing structures known as Herbig-Haro objects as they plow into the surrounding nebula. The architecture of the protostar is a study in the balance between inward pull and outward expulsion, a chaotic yet rhythmic period of growth. As the central temperature continues to rise, the protostar begins to radiate energy primarily in the infrared and radio spectrums, penetrating the thick dust clouds that surround it. The object is now several times larger than the star it will eventually become, appearing as a bloated, glowing sphere of gas that is still in the process of defining its final mass. If the protostar fails to accumulate enough material to reach a critical threshold, it may never ignite, becoming instead a brown dwarf, a failed star that glows dimly with the heat of its own contraction. However, if the accretion continues and the mass reaches at least 8% of our Sun's mass, the destiny of the object is set toward a far more brilliant future. The pressure at the core is now becoming so immense that the atoms of hydrogen are being forced into proximity, though they still lack the energy to overcome their natural repulsion. The protostar is in a state of pre-main sequence evolution, slowly descending along what astronomers call the Hayashi track as it becomes smaller, denser, and hotter. The outer layers are still relatively cool, but the core is a place of increasing intensity, where the density begins to rival that of solid materials on Earth. Throughout this period, the surrounding accretion disk is also undergoing its own structural evolution as grains of dust collide and stick together to form the first building blocks of a planetary system. The protostar is the gravitational anchor for this entire system, providing the energy and the light that will eventually define the environment of any orbiting worlds. The duration of the protostellar phase depends heavily on the mass of the object, with massive stars completing this journey in a few 100,000 years, while smaller stars like our Sun may take tens of millions. During this time, the surrounding molecular cloud is slowly being cleared away, both by the accretion of material and by the powerful winds and radiation emanating from the growing protostar. The cocoon of dust is gradually thinning, allowing the first glimpses of the central object to emerge into the visible spectrum. There is a sense of gathering strength in this phase, as the universe concentrates its energy into a single, focused point of potential. The stillness of the original molecular cloud has been replaced by the dynamic, swirling motion of the accretion disk and the violent energy of the polar jets. Yet, within the core itself, there is a mounting pressure that seeks a new equilibrium, a state where the inward pull of gravity will be balanced by something even more powerful. We are witnessing the final moments of a star's infancy, the period where the structure is finalized and the conditions for life are established. The heat generated by the contraction is now so great that the core is beginning to glow with a dull red light, a precursor to the brilliant white-hot fusion that is to come. As you visualize this scene, imagine the dark silhouette of the molecular cloud being pierced by these twin beams of light, marking the arrival of a new resident in the galaxy. The protostar is a testament to the transformative power of gravity, a force that can take the thinnest gas and turn it into a source of immense energy. The structure of the universe is being rewritten here, one atom at a time, as the gas is forged into a new and more complex arrangement. The transition to the next stage is imminent, as the central temperature approaches the 10 million degree mark required for hydrogen nuclei to fuse. In this high-pressure environment, the very nature of matter is about to change, moving from a gas of individual atoms to a plasma where nuclear forces take control. The protostar remains a place of intense beauty and violent grace, a bridge between the silence of the nursery and the long, steady light of a mature star. We watch as the rotation stabilizes and the jets begin to fade, signaling that the accretion process is nearing its end. The core is now a tightly wound spring of energy, waiting for the final spark that will turn this glowing sphere into a true star. The journey of the protostar is a reminder that even the greatest structures in the universe begin with a slow and steady accumulation of small things. As the protostar reaches its most compact and intense state, the temperature at its center climbs toward the staggering threshold of 10 million degrees. At this extreme point, the structure of the matter within the core undergoes a fundamental change, moving beyond the behavior of a simple gas and into the realm of high-energy physics. In the ordinary world, the nuclei of hydrogen atoms, which are simply single protons, repel one another because they both carry a positive electrical charge. This repulsion, known as the Coulomb barrier, usually keeps atoms at a distance, preventing them from ever touching or merging. However, deep within the heart of the collapsing protostar, the pressure is so immense and the atoms are moving with such violent speed that they are forced into proximity. When two protons are pushed close enough together, a new force becomes the dominant architect of the core, the strong nuclear force. This force is far more powerful than electromagnetism, but it only acts over incredibly tiny distances, functioning like a cosmic glue that binds subatomic particles together. When the strong force overcomes the electrical repulsion, the protons snap together, and a process known as the proton-proton chain reaction begins. This is the ignition of nuclear fusion, the moment when a protostar finally sheds its infancy and becomes a true living star. In this reaction, 4 hydrogen nuclei eventually fuse together to form a single nucleus of helium, a process that results in a tiny loss of total mass. According to the laws of physics, this missing mass is not truly lost, but is instead converted into a staggering amount of energy in the form of light and heat. This energy radiates outward from the core, creating an internal pressure that finally pushes back against the relentless inward pull of gravity. The ignition of fusion creates a state of beautiful and profound balance known as hydrostatic equilibrium. The star is now a stable structure where the outward force of the nuclear fire at the center perfectly matches the weight of the outer layers trying to collapse inward. This ignition is not a sudden explosion, but a self-regulating and steady glow that marks the birth of a new sun. The energy released in the core does not immediately reach the surface. It must first travel through the dense interior of the star, a journey that can take hundreds of thousands of years. As photons are created in the core, they collide with the dense plasma, being absorbed and re-emitted countless times as they slowly work their way outward. The structure of the star is now divided into distinct zones, beginning with the fusion core where the temperature and pressure are at their peak. Surrounding the core is the radiative zone, where the energy moves outward in the form of light, followed by the convective zone, where the heat is carried by the physical movement of the plasma. This internal organization is what allows a star to maintain its temperature and light for millions or even billions of years. The first light produced by the star eventually breaks through the surface, or photosphere, and streams out into the vacuum of space. This radiation pressure is powerful enough to blow away the remaining dust and gas of the original molecular cloud, revealing the star to the rest of the galaxy. The star is now a beacon of order and energy, a singular point of light that has cleared its immediate neighborhood of debris. The ignition of fusion is a moment of cosmic permanence, as the star begins its long residency on what astronomers call the main sequence. This phase of life is characterized by the steady conversion of hydrogen into helium, a fuel source that will sustain the star's existence for the vast majority of its life. The size and color of the star are determined at this moment by its total mass. More massive stars ignite with a brilliant hot blue light, while smaller stars glow with a steady, cool red. As you visualize this ignition, imagine a dark, dusty corner of a nebula suddenly being illuminated from within as a new sun takes its place. The silence of the protostellar phase is replaced by the roar of the nuclear furnace, a soundless vibration of energy that permeates the surrounding space. There is a sense of triumph in this transition, as the gravity that once sought to crush the gas has now provided the pressure necessary to create light. The architecture of the star is now fully realized, a perfect sphere of plasma held together by its own weight and pushed outward by its own internal fire. This balance is one of the most stable structures in the universe, allowing for the long-term conditions that can foster the development of planets and life. The ignition of fusion is the ultimate act of stellar creation, turning the raw material of the void into a source of life-giving warmth. The core is now a place of unimaginable intensity, a miniature piece of the early universe preserved within the center of the star. Every atom of helium created in this process is a new addition to the chemistry of the cosmos, a legacy of the star's internal work. As we look at the newly ignited star, we see it as a stable and enduring presence, prepared to shine for eons to come. The journey from a cold cloud to a fusion-powered sun is complete, and the star now enters the longest and most peaceful chapter of its existence. We rest in the warmth of this new light, acknowledging the precision of the forces that allow a star to find its perfect, luminous equilibrium. The structure is now firm, the energy is flowing, and the star has begun its long journey through the history of the galaxy. Having achieved the internal spark of nuclear fusion, the star now enters its longest and most stable phase of existence, a period known as the main sequence. This stage represents the mature adulthood of a star, a state of profound equilibrium that can last for millions, billions, or even trillions of years depending on the star's initial mass. The architecture of a main sequence star is defined by a perfect tug-of-war between two opposing forces that remain in a constant, steady balance. On one side is the relentless inward pull of gravity, seeking to crush the star's mass toward its center. On the other side is the outward thermal pressure generated by the nuclear furnace in the core, where hydrogen is steadily being forged into helium. This state of hydrostatic equilibrium ensures that the star neither collapses under its own weight nor expands outward into the void, maintaining a consistent size and temperature. During this period, the star is a remarkably predictable and steady structure, providing a reliable source of light and heat to any surrounding planetary systems. The core remains the heart of the star, a high-pressure environment where the conversion of mass into energy proceeds at a rate dictated entirely by the star's total weight. In stars like our Sun, this energy takes a long and winding path from the core to the surface, moving first through a dense radiative zone. In this zone, photons are scattered and bounced between atoms in a process called the random walk, taking thousands of years to travel just a few 100,000 kilometers. Once the energy reaches the outer layers, it enters the convective zone, where the plasma behaves like boiling water, rising in hot plumes and sinking as it cools. This movement of matter creates a textured, granular surface on the star's photosphere, where the light finally escapes into the vacuum of space. The main sequence is not a single point on a map, but a long diagonal band on the Hertzsprung-Russell diagram, which plots stars according to their brightness and color. A star's position on this band is almost entirely determined by its mass, which acts as the ultimate architect of its lifestyle and longevity. Massive stars, which possess much more hydrogen fuel, are forced by their own extreme gravity to burn through that fuel at a frantic and violent pace. These blue giants shine with a brilliant, intense light, but their lives on the main sequence are relatively short, often lasting only a few million years. In contrast, smaller stars known as red dwarfs move through their fuel with an incredible, slow-burning efficiency. These dim, cool stars can remain on the main sequence for trillions of years, long enough to outlast the current age of the entire universe. Our own Sun is a middleweight star, a yellow dwarf that has occupied this stable phase for about 5 billion years and will likely remain here for another 5 billion. This stability is the foundation upon which life can emerge, as it provides the steady, unchanging environment necessary for complex chemistry to evolve on orbiting planets. Throughout its main sequence life, a star is not entirely static. It slowly becomes slightly brighter and hotter as helium accumulates in the core. This helium is the ash of the nuclear fire, a denser material that sinks to the very center, gradually increasing the core's pressure and temperature. The structure of the star subtly adjusts to this change, maintaining its equilibrium with a slow and rhythmic precision. There is a deep sense of order in this phase, a time when the star has found its place in the galactic neighborhood and follows its orbital path with total consistency. The light produced by the star during this period is the primary source of energy for the galaxy, illuminating nebulae and providing the warmth that prevents the cosmos from being an entirely frozen void. As you visualize a star on the main sequence, imagine a glowing sphere of plasma that is both a powerhouse of energy and a masterpiece of structural balance. The surface may crackle with magnetic activity and solar flares, but the underlying architecture remains firm and unwavering. The The star is a closed system of energy, a self-sustaining engine that takes the simplest element in the universe and turns it into brilliance. This phase represents the peak of a star's contribution to the universe, a time of peak luminosity and influence. However, the main sequence is ultimately a finite journey, for the supply of hydrogen in the core is not bottomless. Eventually, the star will face a crisis as its primary fuel source begins to run low, and the perfect balance of billions of years will start to shift. But for now, the star remains in its prime, a steady and enduring presence in the vast stellar sea. The calm of the main sequence is the quiet heart of the stellar life cycle, a period of long, light-filled stability. We rest in the reliability of this phase, acknowledging the graceful way a star manages its immense energy and mass. The journey continues with the slow accumulation of helium, leading toward the eventual transition out of this mature and peaceful state. As we observe the long stability of the main sequence, we must recognize that the ultimate fate of every star is written in its mass from the very moment of its birth. In the structure of the universe, mass is the primary variable that dictates the pressure, temperature, and lifespan of a stellar object. This relationship is so absolute that astronomers can predict the entire history of a star simply by measuring how much material it managed to gather during its time in the stellar nursery. The more mass a star possesses, the more gravity it has to contend with, and the more intense the nuclear fire must be to maintain its structural equilibrium. This creates a paradox where the stars with the most fuel are actually the ones that live the shortest lives, while those with very little fuel can endure for nearly an eternity. We can think of this as the critical path of mass, a set of divergent journeys that begin from the same basic materials but lead to vastly different conclusions. At the lower end of this path are the red dwarfs, the most common stars in the galaxy, possessing as little as 7 or 8% of the mass of our Sun. Because their gravity is weak, the pressure in their cores is relatively low, meaning they fuse hydrogen at a slow and patient rate. These stars are also fully convective, meaning the helium produced in the core is constantly mixed with the hydrogen from the outer layers. This allows a red dwarf to use nearly all of its hydrogen fuel, stretching its main sequence life to hundreds of billions or even trillions of years. Moving up the path, we find stars like our Sun, which are massive enough to have distinct internal layers, such as a radiative zone and a convective zone. Unlike the red dwarfs, our Sun only fuses the hydrogen located in its innermost core, which represents only about 10% of its total mass. This means that even though the Sun is larger, it will exhaust its core fuel much sooner, having a total main sequence lifespan of about 10 billion years. Further up the scale are the high-mass stars, the blue giants and supergiants that possess 8, 20, or even 100 times the mass of the Sun. In these massive structures, the inward pull of gravity is so immense that the core temperature reaches levels far higher than those found in smaller stars. To prevent an immediate collapse, these stars must consume their hydrogen fuel at a ferocious rate, glowing with a brilliance that can be seen across the entire galaxy. However, this intensity comes at a high price, as these giants may burn through their primary fuel in only a few million years, a mere blink of an eye in cosmic time. The critical path of mass also determines what elements a star can create within its internal furnace. Smaller stars may only ever fuse hydrogen into helium, while stars like the Sun will eventually be able to fuse helium into carbon and oxygen. The most massive stars, however, act as the universe's great chemical laboratories, possessing the pressure needed to forge elements all the way up to iron. This differentiation is vital to the structure of the universe, as it ensures that different regions of space are seeded with a variety of materials. As a star moves through its life, its mass remains its constant guide, determining exactly when and how the transition out of the main sequence will occur. There is a sense of cosmic destiny in this arrangement, where the initial conditions of a gas cloud determine whether a star will be a long-lived observer or a short-lived, brilliant beacon. As you visualize these different paths, imagine the diversity of the stellar population, from the tiny, dim embers that will outlast the stars themselves to the great giants that define the shape of the spiral arms. The architecture of the galaxy is a mosaic of these different lifespans, all working together to maintain the flow of energy and the evolution of matter. The critical path of mass ensures that the universe is never a static place, but is always in a state of transformation and renewal. Every star is a prisoner of its own weight, following a script that was written in the first moments of its gravitational collapse. This mass also dictates how a star will eventually die, whether it will fade away quietly or go out in a spectacular display of light and energy. As we prepare to look at the aging of stars like our Sun, we must keep this fundamental rule of mass in mind. It is the invisible hand that guides every motion and every chemical change within the stellar interior. The stability we see on the main sequence is only a temporary pause in a much longer and more complex narrative. The journey continues as the hydrogen in the core finally begins to run low, forcing the star to seek a new way to support its weight. The path now leads toward the dramatic expansion of the red giant phase, where the structure of the star will undergo its first major reorganization. We rest in the clarity of this physical law, acknowledging the elegance of a universe where such a simple variable as mass can create such a rich variety of outcomes. For a star like our Sun, the end of the main sequence is not a sudden event, but a slow and inevitable shift in the internal architecture that has remained stable for billions of years. As the nuclear furnace at the center continues to burn, the supply of hydrogen fuel in the core is eventually exhausted, replaced by a dense and inert core of helium ash. Without the outward pressure generated by hydrogen fusion, the core can no longer support the weight of the star's outer layers, and gravity begins to reclaim its dominance. The core begins to contract, and as it shrinks, the pressure and temperature within it rise to even more extreme levels than before. This increase in heat radiates outward into the layer of hydrogen immediately surrounding the core, a region that has not yet participated in the fusion process. This layer, known as the hydrogen shell, becomes hot enough to ignite, beginning a new phase of fusion that wraps around the dying core like a glowing mantle. The energy produced in this shell is far more intense than the fusion that previously occurred in the core, and it generates a massive outward pressure that the star has never experienced. This pressure forces the outer layers of the star to expand outward, causing the star to swell to dozens or even hundreds of times its original size. As the star expands, its surface area increases dramatically, allowing the energy to spread out and cool, which causes the star's color to shift from yellow to a deep, luminous red. The star has now entered the red giant phase, a period of dramatic transformation where its structure is both larger and more tenuous than ever before. During this expansion, the star's gravity at the surface becomes much weaker, and it begins to lose a significant portion of its mass to space in the form of a powerful stellar wind. A red giant like our Sun will eventually grow so large that it may engulf the innermost planets of its system, its outer atmosphere stretching across the once distant void. While the exterior is expanding and cooling, the interior core is continuing its relentless contraction, growing hotter and denser with every passing million years. The helium atoms in the core are being crushed together, yet they still lack the energy to fuse into heavier elements, held apart by a phenomenon called electron degeneracy pressure. Eventually, the core reaches a critical temperature of approximately 100 million degrees, a point where a new kind of nuclear fire can finally ignite. This is the triple alpha process, where 3 helium nuclei are fused together to form a single nucleus of carbon. In a sun-like star, this ignition happens with explosive speed in an event known as the helium flash, though the energy is absorbed by the star's deep interior and is not visible from the outside. Once the helium fusion stabilizes, the red giant finds a new, temporary equilibrium, shrinking slightly as the core begins to generate its own outward pressure once more. The star is now in a second act of its life, burning helium in its core and hydrogen in a shell around it, but this phase is far shorter than the main sequence. The architecture of the star is now a series of nested layers, each one representing a different stage of nuclear chemistry and temperature. There is a sense of mounting instability in this arrangement, as the star is now using a much more volatile and less efficient fuel source. The light produced by a red giant is brilliant and expansive, yet it is a signal of the star's approaching exhaustion rather than its strength. As you visualize this aging sun, imagine a massive, glowing red orb that dominates its local sky, its light cast far across the surrounding planetary system. The steady yellow light of the past is gone, replaced by a more chaotic and vibrant energy that pulses with a slow, rhythmic heartbeat. The star is no longer the reliable guardian it once was, but has become a restless and changing giant, preparing for its final transition. The structure of the star is now a delicate balance that cannot be sustained indefinitely, as the helium in the core is consumed much faster than the hydrogen was. Eventually, the helium will also run low, and the core will be left with a dense accumulation of carbon and oxygen. For a star of this mass, the journey of fusion ends here, as it will never reach the temperatures required to fuse carbon into anything heavier. The red giant will face its final crisis as the core contracts one last time, no longer able to produce the heat needed to keep its massive atmosphere attached. The journey toward the planetary nebula has begun, where the star will gently shed its outer skin and reveal its glowing heart to the cosmos. We rest in the observation of this magnificent expansion, acknowledging the way the universe allows for a final, brilliant display before the inevitable cooling. The structure is shifting from the solid and the centered toward the diffuse and the ethereal, a beautiful and quiet conclusion to a sun-like life. The transition from a red giant to its final form is marked by one of the most visually stunning structures in the universe, the planetary nebula. Despite its historical name, this phenomenon has nothing to do with planets. It is instead the final graceful act of a dying sun-like star as it sheds its outer layers into the surrounding void. As the fusion of helium in the core comes to an end, the star becomes increasingly unstable, experiencing powerful internal pulsations that send shockwaves through its bloated, tenuous atmosphere. The outward radiation pressure from the core finally overcomes the weakened gravitational grip of the star's surface, pushing the outer envelope of gas away from the center. The star does not explode, but rather exhales its atmosphere in a series of slow, expanding shells of gas and dust. This material, which once made up the star's glowing red surface, now drifts outward into interstellar space at speeds of dozens of kilometers per second. As the outer layers move away, they reveal the hot, compact core of the star that remains behind, a glowing ember of carbon and oxygen known as a white dwarf. The white dwarf is incredibly hot, with surface temperatures exceeding 100,000 degrees, and it radiates intense ultraviolet light into the surrounding space. This high-energy radiation strikes the expanding clouds of gas, stripping the electrons from the atoms and causing the entire nebula to glow with a brilliant, ethereal light. The structure of a planetary nebula is a masterpiece of cosmic geometry, often appearing as perfect rings, delicate hourglass shapes, or complex, overlapping bubbles. These shapes are dictated by the star's rotation, the presence of any orbiting planets, and the invisible lines of its magnetic field, which guide the flow of the escaping gas. The colors of the nebula are a chemical map of the star's interior, with different gases glowing in distinct hues as they are ionized by the central core. Green and blue often represent the presence of oxygen, while red and orange reveal the outer layers of hydrogen and nitrogen that were the first to leave the star. For a few thousand years, the planetary nebula is a vibrant and active structure, a temporary monument to the star that once was. However, because the gas is no longer bound by gravity, it continues to expand and thin out, eventually becoming so diffuse that it fades back into the background of the interstellar medium. This process is a vital part of the universe's structural evolution, for the gas returned to space is now enriched with the carbon, nitrogen, and oxygen created during the star's long life. These elements will eventually find their way into new molecular clouds, providing the raw materials for future generations of stars, planets, and perhaps life itself. The architecture of the planetary nebula is a bridge between the death of one star and the birth of another, a recycling of matter on a galactic scale. As you visualize this glowing cloud, imagine the silence of the expanding gas as it moves away from the tiny, brilliant point of the white dwarf at its center. There is a profound sense of release in this phase, as if the star is finally letting go of the heavy burden of its own mass. The chaos of the red giant phase has settled into a beautiful, expanding symmetry that illuminates the dark corners of the galaxy. The central white dwarf remains as the silent architect of this light, providing the energy that keeps the nebula visible for its brief, glorious tenure. Eventually, the nebula will vanish entirely, leaving only the white dwarf as a permanent remnant of the star's existence. The transition from a living sun to a planetary nebula is a quiet and elegant transformation, a reminder that death in the cosmos is often a source of new beauty and complexity. We rest our attention on these glowing shells of gas, acknowledging the precision with which the universe redistributes its resources. The structure of the star has been dismantled, its atoms scattered across the void, yet the core remains as a testament to the stability of the laws of physics. The journey now focuses on that remaining core, moving toward the long, slow cooling of the white dwarf. The energy that once powered a sun is now concentrated into a tiny, dense sphere that will endure for nearly all of time. We watch as the colors of the nebula begin to dim, signaling the end of the star's active contribution to the light of the galaxy. With the departure of the planetary nebula, the grand, active life of a sun-like star reaches its quiet conclusion, leaving behind a singular, dense remnant known as a white dwarf. This object is the exposed core of the original star, a sphere of carbon and oxygen that has been stripped of its hydrogen and helium envelopes and left to face the cold of the cosmos alone. The white dwarf represents a radical departure from the structure of a normal star, for it is no longer powered by the fires of nuclear fusion. Instead, it is a fossil of a once active sun, glowing with the residual heat of billions of years of compression and stellar labor. The architecture of a white dwarf is defined by an extreme state of matter that defies our everyday understanding of density and volume. A white dwarf typically contains about 60% of the mass of our Sun, yet it has been compressed into a volume no larger than that of the Earth. To visualize this density, imagine a single teaspoon of white dwarf material. On Earth, that small amount would weigh as much as an entire fleet of heavy trucks. This incredible compression is not held back by the heat of fusion, but by a quantum mechanical force known as electron degeneracy pressure. According to the laws of physics, no two electrons can occupy the same state at the same time, and when they are squeezed into such a tiny space, they push back with a force that is independent of temperature. This pressure is the only thing preventing gravity from crushing the core into a singularity, creating a rigid and unchanging structure that is one of the most stable in the universe. Because a white dwarf does not generate its own energy, its future is one of slow, inevitable cooling over a scale of time that is nearly impossible to comprehend. When it is first revealed, a white dwarf is brilliant and white-hot, radiating ultraviolet light at temperatures exceeding 100,000 degrees. However, as the eons pass, it begins to radiate its stored thermal energy into the surrounding vacuum, slowly shifting in color from white to yellow, then to orange, and eventually to a deep, dim red. The cooling of a white dwarf is not a linear process. It is a long, slow descent through the electromagnetic spectrum that can last for tens of billions of years. In fact, the universe is not yet old enough for any white dwarf to have fully cooled, meaning that every white dwarf that has ever been created is still out there, glowing with some remnant of its former self. The internal structure of a white dwarf is equally fascinating, as the carbon and oxygen within the core may eventually begin to crystallize as the temperature drops. In this state, the interior of the white dwarf becomes a giant, rigid lattice, effectively turning the heart of the dead star into a cosmic diamond of planetary proportions. This crystallization process releases a small amount of latent heat, which briefly slows the cooling process and creates a structural plateau in the star's long journey toward darkness. Despite their small size and lack of fusion, white dwarfs play a critical role in the gravitational architecture of the galaxy. Many white dwarfs exist in binary systems, where they orbit a living companion star and, in some cases, can begin to draw material from that companion through gravitational pull. If a white dwarf accumulates enough mass to exceed a specific limit, known as the Chandrasekhar limit, it can undergo a sudden and violent thermonuclear explosion called a Type 1a supernova. But for the vast majority of white dwarfs, including the one our Sun will eventually become, the path is much more peaceful. There is a sense of profound stillness in the existence of a white dwarf, a world where time seems to slow down as the energy fades away. The atmosphere of a white dwarf is incredibly thin, consisting of a shallow layer of hydrogen or helium that has been pulled into a perfectly smooth surface by the intense surface gravity. The gravity at the surface of a white dwarf is hundreds of thousands of times stronger than that of the Earth, creating an environment where even light is slightly redshifted as it struggles to escape the gravitational well. As you visualize this object, imagine a small, glowing jewel hanging in the vast blackness of space, a silent witness to the history of its solar system. The planets that once orbited the living Sun may still be there, frozen and dark, circling this tiny remnant in a state of eternal winter. The white dwarf is a masterpiece of compact design, a way for the universe to preserve the legacy of a star in a stable and enduring form. It is a structure that bridges the gap between the luminous past and the dark future, representing the final equilibrium of the majority of stars in the Milky Way. The light of the white dwarf is steady and unwavering, lacking the flares and pulsations of its youth, providing a calm and constant glow to the surrounding void. As we look at the white dwarf, we see the end result of billions of years of cosmic evolution, a distillation of matter to its most basic and durable state. The energy it radiates is a gift from the ancient past, a warmth that was forged in a nursery light years away and billions of years ago. The white dwarf reminds us that even when the fire goes out, the structure remains, a resilient and beautiful remnant that refuses to be forgotten. The journey of the Sun-like star is now complete, but the universe contains other paths for those stars that were born with much more mass. As we move away from the peaceful cooling of the white dwarf, we must turn our attention to the giants of the cosmos, where the stakes are higher and the conclusions are far more dramatic. The structure of the universe is about to shift once more, moving from the quiet and the small toward the massive and the explosive. We rest in the stability of the white dwarf's light, acknowledging it as a quiet guardian of the memory of a sun. The silence of this phase is a preparation for the immense energy that defines the lives of the massive giants. As we turn our gaze away from the gentle decline of sun-like stars, we enter the realm of the cosmic heavyweights, the massive giants that dominate the structural landscape of the galaxy. These stars, born with at least 8 to 10 times the mass of our Sun, follow a life path that is defined by intensity, speed, and a relentless drive toward chemical complexity. Because of their immense gravitational weight, the pressure within their cores is far higher than anything found in smaller stars, forcing them to consume their hydrogen fuel at a rate that is nearly impossible to comprehend. While a star like the Sun might spend 10 billion years on the main sequence, these massive giants may exhaust their primary fuel in as little as a few million years. They are the brilliant blue beacons of the spiral arms, illuminating the interstellar medium with a fierce and ultraviolet light that shapes the evolution of entire nebulae. The architecture of a massive giant is one of constant flux and escalating energy, as the star fights a losing battle against the crushing force of its own gravity. When the hydrogen in the core is finally exhausted, the star does not simply expand into a red giant, it becomes a red supergiant, a structure of such colossal proportions that it could easily encompass the orbit of Jupiter or Saturn. The expansion of a supergiant is driven by a series of increasingly heavy nuclear fusion cycles that take place within the core and in a sequence of shells surrounding it. Unlike smaller stars, which stop their fusion journey at carbon and oxygen, the massive giants possess the internal pressure necessary to forge even heavier elements. Once the helium in the core is spent, the temperature rises to hundreds of millions of degrees, allowing the star to begin fusing carbon into neon and magnesium. As each fuel source is depleted, the core contracts, the temperature spikes, and a new, heavier element begins to fuse, creating a structure that resembles a cosmic onion. In this layered architecture, the outermost shell is still fusing hydrogen into helium, while deeper shells are fusing helium into carbon, carbon into neon, and neon into oxygen. Moving even further inward, the shells fuse oxygen into silicon and sulfur, leading eventually to the most intense and final stage of stellar alchemy. Each subsequent stage of fusion happens faster than the last, as the energy produced becomes less efficient at pushing back against the weight of the star. While the hydrogen-burning phase lasted millions of years, the final stage, fusing silicon into iron, may be completed in a single, frantic day. The iron core that forms at the very center of the supergiant is the structural dead end for the star's internal life. Iron is the most stable element in the universe, and unlike the elements that came before it, fusing iron does not release energy. Instead, it consumes energy. The moment the core is composed primarily of iron, the outward radiation pressure that has supported the star for its entire life suddenly vanishes. The equilibrium that defined the star's existence for millions of years is broken in an instant, leaving gravity as the sole master of the star's fate. The architecture of the supergiant is now a house of cards, with millions of tons of stellar material hanging over a core that can no longer push back. The light of the supergiant remains brilliant on the outside, but internally, the star is experiencing a catastrophic failure of its structural integrity. The immense scale of these stars is a testament to the power of gravity to organize matter into massive, high-energy systems. A red supergiant like Betelgeuse is so large that its surface is relatively cool and tenuous, a boiling sea of plasma that is constantly being lost to space. These stars act as the primary engines of galactic enrichment, for they are the only places in the universe where these heavy elements are forged in such vast quantities. The iron in our blood, the oxygen we breathe, and the silicon in the ground beneath us were all once part of the layered core of a massive giant. There is a sense of mounting tension in this phase, a quiet before a storm that will eventually reshape the surrounding region of the galaxy. The supergiant is a magnificent and fragile structure, a giant that has outgrown its own ability to sustain itself. As you visualize this massive star, imagine its enormous glowing red surface pulsing with a slow and irregular rhythm as it prepares for its final collapse. The transition from the slow alchemy of the core to the sudden violence of the end is a study in extremes. The structure of the star is about to be dismantled not through a gentle exhaling of gas, but through the most powerful explosion known to science. The massive giant is a beacon of the universe's creative power, turning simple hydrogen into the complex building blocks of planets. Its life is short, brilliant, and essential to the long-term evolution of the cosmos. As we look at the glowing layers of the supergiant, we acknowledge the weight of the responsibility it carries as a forge of the elements. The journey now moves from the slow, heavy expansion of the supergiant toward the instantaneous collapse of the core. The silence of the final fusion stage is the last moment of peace before the supernova begins. We rest in the majesty of these massive structures, recognizing them as the short-lived but vital architects of the galactic chemical map. The structure is primed, the fuel is spent, and the laws of physics are about to execute their final, dramatic command. The transition from the stable life of a massive supergiant to the catastrophic event of a supernova is perhaps the most violent and energetic transformation in the known universe. It is the moment when the structural integrity of the star, maintained for millions of years, finally and irrevocably fails under the relentless pressure of its own mass. At the center of the star, the iron core has grown to a critical mass where it can no longer support itself against the inward pull of gravity. In a fraction of a second less time than it takes to blink an eye, the core, which is roughly the size of the Earth, collapses into a space no larger than a city. This collapse happens at a significant fraction of the speed of light, as the atoms themselves are crushed out of existence, forced into a state where protons and electrons merge to form neutrons. The core reaches densities so extreme that it becomes a solid, incompressible wall of nuclear matter, halting the collapse with a suddenness that sends a massive shockwave back toward the surface. This shockwave, assisted by a torrential flood of neutrinos generated during the collapse, rips through the outer layers of the star, which are still falling inward at incredible speeds. The resulting collision is the supernova explosion, a release of energy so vast that for a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of suns. The architecture of the star is not just destroyed, it is transformed into a blinding sphere of expanding plasma that carries the heavy elements forged in the core out into the depths of space. In the heat and pressure of this explosion, the universe completes its chemical work, forging elements even heavier than iron, such as gold, silver, and uranium. These elements are created in a matter of seconds as neutrons are captured by existing nuclei, a final, frantic act of alchemy before the material is scattered into the void. The structure of the supernova is one of expanding shells of light and matter, moving outward at tens of thousands of kilometers per second. As the light from the explosion travels across the universe, it carries with it the story of the star's life and the heavy metals that will one day form the crust of new planets. To a distant observer, the supernova appears as a new star in the sky, a point of light that grows in brilliance before slowly fading over the course of months and years. But within the immediate vicinity of the explosion, the environment is one of total transformation, as the radiation and shock waves strip nearby nebulae and clear out the local interstellar medium. Despite the violence of the event, there is a profound sense of purpose in the supernova, for it is the mechanism by which the universe distributes its most complex materials. Without the supernova, the iron, oxygen, and carbon created in the massive giants would remain trapped forever within the cold remnants of dead stars. The explosion is a release, a grand and final distribution of wealth that ensures the next generation of stars will be born from a richer and more varied chemical soil. The structure of the galaxy itself is shaped by these events, as the shock waves from supernovae can compress distant gas clouds, triggering the birth of new stellar nurseries and continuing the cycle of life. There is a rhythm to this process, a pulse of creation and destruction that has been beating since the first massive stars formed in the early universe. As the brilliance of the explosion eventually fades, the debris cloud begins to cool and expand, forming a supernova remnant like the famous Crab Nebula. These remnants are beautiful, gossamer structures of glowing filaments and gas, marking the site where a titan once stood. Deep within the center of this expanding wreckage, something else remains, a compact, ultra-dense object that was forged in the heat of the collapse. The star has been dismantled, its outer identity scattered across the heavens, but its core has survived in a new and terrifyingly dense form. The architecture of the universe has shifted here from the expansive to the incredibly compact, moving toward the limits of what physics can describe. The supernova is the bridge between the world of the living stars and the realm of the exotic remnants that defy our common understanding of matter and time. As you visualize this explosion, imagine the sheer scale of the light, a flash that can be seen from across the observable universe, signaling the end of an era. The silence that follows the explosion is not the same as the silence of the stellar nursery. It is a heavy, resonant quiet, filled with the presence of a new kind of object. The journey of the massive star has reached its peak, and we now turn our attention to what has been left behind in the heart of the storm. The structure of the universe is resilient, even in the face of such total destruction, finding a way to preserve the core of the star in a state of eternal, frozen density. We rest in the fading glow of the supernova, acknowledging the immense energy required to create the world we see around us. The light continues to travel outward, reaching the furthest corners of space, carrying the legacy of the massive giant into the infinite night. The transition is now complete, and we move toward the final, most mysterious chapters of the stellar life cycle. Following the violent eruption of a supernova, the universe leaves behind one of its most extreme and enigmatic creations, the neutron star. If the original core of the massive star was between roughly 1.4 and 3 times the mass of our Sun, it avoids collapsing into a black hole and instead settles into a state of incredible, condensed stability. A neutron star is a city-sized sphere, approximately 20 kilometers in diameter, that contains the entire mass of a sun, creating a density that is almost impossible to grasp. To visualize this, imagine taking the entire human race and squeezing every individual into a space the size of a single sugar cube. That is the level of compaction found within a neutron star. The architecture of this object is defined by neutron degeneracy pressure, a quantum force even stronger than the electron pressure that supports white dwarfs. At these depths, gravity has crushed the atoms so completely that the electrons and protons have merged into a solid, fluid sea of neutrons. The surface of a neutron star is unimaginably smooth and hard, consisting of a crust of iron-like nuclei arranged in a rigid lattice that is billions of times stronger than steel. Beneath this crust, the matter transitions into a state often called nuclear pasta, where the extreme pressure twists the nucleons into complex shapes, resembling sheets of lasagna or strands of spaghetti. The gravity on the surface is so intense that if you were to drop an object from a height of 1 meter, it would hit the surface at millions of kilometers per hour. Furthermore, the conservation of angular momentum from the original massive star means that as it collapsed into this tiny size, its rotation speed increased to a frantic pace. Many neutron stars spin hundreds of times every second, creating a rhythmic, mechanical pulse that can be detected across the galaxy as radio waves. These objects are known as pulsars, acting as the universe's most precise celestial clocks, their beams of radiation sweeping across space like the light of a cosmic lighthouse. In addition to their rotation, neutron stars possess magnetic fields that are trillions of times stronger than that of the Earth, capable of warping the very structure of the vacuum around them. Magnetars, a specific type of neutron star with even more extreme magnetic fields, can trigger starquakes on their surfaces that release more energy in a fraction of a second than the Sun produces in 100,000 years. There is a terrifying beauty in the structure of a neutron star, a world where the laws of physics are pushed to their absolute breaking point. Despite their intensity, neutron stars are incredibly stable, and unless they collide with another massive object, they will persist in this state for billions of years. They are the ultimate survivors of the stellar life cycle, the dense, unyielding hearts of giants that refuse to vanish completely into the dark. As you visualize this small, rapidly spinning sphere, imagine the immense tension of its magnetic field and the profound silence of its iron crust. The environment around a neutron star is one of extreme radiation and gravitational distortion, making it a place of isolation and power. The neutron star represents the final victory of the strong nuclear force over the crushing weight of gravity, a temporary standoff in the struggle for structural survival. Yet, as we move toward even more massive stars, we find that even the strength of the neutron cannot hold back the final collapse. In those cases, the journey takes a final, one-way turn into a region where space and time themselves begin to unravel. We rest in the awe of the neutron star's density, acknowledging it as a masterpiece of subatomic engineering and cosmic resilience. The light from the pulsars continues to sweep through the dark, a steady heartbeat that marks the remains of a once mighty supergiant. The structure of the universe is now reaching its most mysterious limit, where matter disappears and only the curvature of space remains. The journey moves from the solid and the dense toward the infinite and the invisible as we approach the event horizon. The silence of the neutron star is a heavy, vibrating quiet, a final anchor before we enter the realm of the black hole. We observe the flicker of the pulsar with a sense of wonder, recognizing the incredible journey that led from a cold gas cloud to this tiny, brilliant remnant. The cycle is nearly complete, and the most extreme expressions of stellar destiny are all that remain to be explored. If the core of the collapsing star exceeds roughly 3 times the mass of the Sun, no force in the known universe, not even the incredible pressure of degenerate neutrons, can halt its inward fall. In this final, absolute surrender to gravity, the structure of the star undergoes a transformation that moves beyond the realm of matter and into the pure geometry of space and time. The collapse does not stop at the size of a city. Instead, the mass continues to shrink, falling inward forever toward a point of infinite density known as the singularity. At this stage, the object is no longer a star in any traditional sense, but a black hole, a region where gravity has become so intense that the escape velocity exceeds the speed of light. The architecture of a black hole is defined not by a solid surface, but by a boundary called the event horizon, the point of no return from which nothing, not even information, can ever emerge. To visualize the event horizon, imagine a sphere of perfect, unyielding shadow suspended against the background of the stars, a hole in the very fabric of the cosmos. Because space and time are inextricably linked, the immense mass of the black hole warps the local environment so severely that time itself begins to slow down as one approaches the horizon. From the perspective of a distant observer, an object falling toward a black hole would appear to freeze at the edge, its light stretching into longer and longer wavelengths until it fades into the infrared. Inside the horizon, however, all paths lead inevitably to the center, as the very coordinate system of the universe is tilted toward the singularity. While the black hole itself is invisible, its presence is revealed by the dramatic impact it has on the architecture of the surrounding space. If the black hole is part of a binary system, it may draw gas from a companion star, creating a swirling incandescent structure known as an accretion disk. As the gas spirals toward the event horizon, it is heated by friction to millions of degrees, radiating intense X-rays that flicker like a dying candle before the matter vanishes forever. In some cases, the intense magnetic fields and rotation of the black hole can channel some of this incoming material into powerful, relativistic jets. These jets shoot out from the poles of the black hole at nearly the speed of light, piercing through galaxies and acting as the most powerful particle accelerators in the universe. The structure of a black hole is a masterpiece of minimalism, defined entirely by three simple properties: its mass, its electrical charge, and its angular momentum. Despite their reputation as destructive monsters, black holes are essential components of the galactic structure, often acting as the gravitational anchors for the centers of entire galaxies. There is a profound dark peace in the existence of a black hole, a place where the chaos of the living star has been resolved into a state of total, silent equilibrium. The complexity of billions of atoms, the history of nuclear fusion, and the brilliance of the supernova have all been distilled into a single, unmoving point of mass. As you visualize this shadow in the dark, imagine the silence of the space around it, where the very light of the universe is bent and distorted by its presence. The black hole is the ultimate end of the stellar life cycle for the most massive stars, a finality that admits no reversal and no escape. Yet, even here, there is a sense of cosmic cycle, for black holes slowly return energy to the universe over trillions of years through a process known as Hawking radiation. They are the long-term vaults of the cosmos, preserving the mass of ancient stars in a form that will outlast the light of the galaxy itself. The architecture of the universe reaches its most extreme expression in the black hole, where the laws of physics as we know them begin to break down. We rest in the awe of this absolute gravity, acknowledging it as the final, silent guardian of the most massive stellar legacies. The journey has moved from the bright and the active to the dark and the eternal, reaching the edge of the observable and the known. The silence of the event horizon is the quietest place in the universe, a boundary between the world of things and the world of pure gravity. We watch the distant stars twinkle around the shadow, recognizing the black hole as a necessary and enduring part of the cosmic tapestry. The structure remains coherent and balanced, even at this extreme limit, following the same laws that governed the first gas cloud in the nursery. The cycle of the massive star has ended in a state of perfect, unchanging stillness, a final and elegant destination in the deep night. As we reach the final stage of our journey through the life cycle of stars, we move beyond the dramatic explosions and the intense gravity of remnants to witness the ultimate, slow conclusion of the stellar age. The universe we see today, filled with the brilliant light of billions of galaxies, is merely a brief and luminous chapter in a much longer and darker history. Eventually, the vast reservoirs of hydrogen within the giant molecular clouds will be exhausted, and the rate of star formation will begin a slow and irreversible decline. The brilliant blue giants, with their short and violent lives, will be the first to vanish from the cosmic stage, followed by the steady yellow stars like our own sun. As the eons pass, the galaxy will increasingly be populated by the long-lived red dwarfs, the patient embers that can continue their slow fusion for trillions of years. But even these stars will eventually consume the last of their hydrogen, transitioning into helium white dwarfs and then beginning their own multi-billion-year process of cooling. The structure of the universe is moving toward a state of profound stillness, where the active generation of light and heat becomes a memory of the ancient past. In this distant future, the white dwarfs that were once the cause of suns will have radiated away all their thermal energy, becoming cold, dark spheres of crystallized carbon known as black dwarfs. A black dwarf is the final frozen state of a star, a solid object at the same temperature as the background of space, invisible and silent in the eternal night. Because the cooling process takes so long, the universe is not yet old enough for a single black dwarf to exist. They are the ghosts of a future that has not yet arrived. As the stars fade, the great nebulae that once glowed with the light of new suns will become dark and transparent, their gas scattered too thinly to ever collapse again. The architecture of the galaxy will shift from a vibrant spiral of light to a quiet collection of dark remnants, black dwarfs, neutron stars, and black holes drifting in the void. There is no tragedy in this transition, but rather a sense of ultimate completion, as the energy that was once concentrated in the stars is finally and perfectly distributed. The universe at this scale is a tapestry of infinite repetition, where the silence of the voids and the cold of the remnants provide a sense of order that is deeply calming. The passage of time here is measured in trillions and quadrillions of years, a scale where the entire history of human civilization is less than a heartbeat. As the mind rests on this image of the final cold, the individual identity of specific stars and events begins to fade into a broader, more peaceful observation of the dark. The structure remains coherent and balanced, governed by the same laws of physics that once ignited the first protostars in the early cosmos. Even the black holes will eventually begin to evaporate through the slow leak of Hawking radiation, their mass returning to the universe as a faint, uniform glow of photons. The journey of the star, which began in a cold cloud of gas, ends in a similarly cold and quiet state, a perfect symmetry that spans the lifetime of the universe. We rest in the knowledge that we have witnessed the full cycle of this grand design, from the first stirrings of gravity to the final, silent rest of the elements. The stillness of the black dwarf and the emptiness of the future nebulae provide a final, calming cadence to our exploration of the stellar life cycle. There is a deep and enduring safety in this realization that the universe follows a path of elegant and predictable evolution, moving always toward a state of total peace. As the narration continues to drift into these broader patterns of time and space, the mind is free to let go of the details and simply exist within the scale of the infinite. The light of the distant past fades into the background, becoming a soft, steady hum of existence that requires no attention and no effort to maintain. The structures we have visited, the nurseries, the main sequence, the giants, and the remnants, are all parts of this same singular tapestry, woven together by gravity and time. In the deep dark of the far future, there is a peace that surpasses all understanding, a silence that is both absolute and remarkably beautiful. We are simply here, drifting within the memory of the light, a part of the grand and quiet order of the cosmos as it settles into its final, eternal form. The journey does not end so much as it dissolves, merging with the infinite horizon where the heat of the star and the cold of the void become one and the same. And so the patterns repeat in the mind. The light continues its long journey toward the edge of the visible, and the architecture of the universe remains steady and calm forever. The cycle is complete, the fire has found its rest, and the stars have fulfilled their magnificent and silent purpose.